Imagine standing outside on the clearest night you have ever seen. The kind of night where the air is so cold and still that every star seems close enough to touch, where the Milky Way spills across the sky like paint poured by a careless god, and where the silence is so complete that you can almost hear the universe breathing. Now imagine that somewhere out there, in a direction you cannot point to with your finger, but that scientists can measure with instruments sensitive enough to detect a whisper across the void of space, there is a hole. Not a hole in the way we normally think about holes. Not a gap in a fence or a tear in a piece of fabric. This is something far stranger, far more unsettling, and far more profound. This is a region of the universe so cold, so vast, and so inexplicably empty that it has confounded some of the greatest scientific minds on the planet for more than 2 decades. It has no name that captures its full strangeness. Scientists call it the cold spot, and the more they look at it, the more it refuses to behave the way anything in our universe should behave. Here is something that might stop you in your tracks if you really let it sink in. The universe is filled with radiation left over from the Big Bang. This radiation, called the cosmic microwave background, or CMB for short, is essentially the afterglow of creation itself. It is the oldest light in the universe, the echo of the moment when everything that exists first came into being from an unimaginably hot, dense point of infinite possibility. This radiation fills every corner of the observable universe. It is, in a sense, everywhere all at once. And for the most part, it is extraordinarily uniform. The temperature variations across the entire CMB are tiny, measured in 100,000ths of a degree. The universe, from this perspective, looks remarkably smooth and even, like a perfectly baked cosmic loaf of bread. But then there is the cold spot. In one particular direction in the sky, in the constellation Eridanus, there is a region where the temperature of the CMB drops significantly below what it should be. Not by a little. Not by an amount that can be easily explained away or tucked into a corner of a theory. The cold spot is approximately 70 microkelvins colder than the average temperature of the CMB, and it covers an area of the sky roughly 5 times the diameter of the full moon. To put that in perspective, if the entire CMB is a canvas painted with incredibly subtle brushstrokes of temperature variation, the cold spot is a place where someone has reached in and erased a section roughly the size of a continent, leaving behind something fundamentally different from everything around it. And here is the question that has been haunting cosmologists, physicists, and astronomers since this anomaly was first confirmed in 2004. What could possibly have caused it? The answers that have been proposed over the years range from the mundane to the utterly mind-bending. Some scientists believe it is a statistical fluke, a random accident in a universe so vast that strange things are bound to happen occasionally. Others believe it could be explained by a supervoid, an enormous region of space that contains far fewer galaxies than it should, a cosmic desert stretching across billions of light years. And then there are those who look at the cold spot and cannot shake the feeling that what they are seeing is something no existing theory within our universe can adequately explain. Something that might require us to consider the most radical idea in all of modern cosmology, that our universe is not the only one. That somewhere, at some point in the deep past, our universe may have collided with another universe entirely, and that the cold spot is the scar left behind. Think about that for a moment. A scar from a collision with another universe. Not a metaphor, not science fiction. A genuine scientific hypothesis put forward by serious researchers at serious institutions using rigorous mathematics and observational data. This is the story of the cold spot. And it is one of the most extraordinary stories ever told about the nature of reality itself. To understand why the cold spot is so significant, you first need to understand the universe in which it exists. You need to go back, further than you have probably ever tried to go before, all the way back to the beginning. Approximately 13.8 billion years ago, there was nothing. Or more precisely, there was something so incomprehensibly different from anything we experience today that calling it nothing is almost more accurate than trying to describe what it actually was. In a single moment, for reasons that physics still cannot fully explain, space and time themselves came into existence. Energy erupted. The universe was born in an event of staggering violence and unimaginable heat. In the first fraction of a second after the Big Bang, the universe was so hot that matter as we know it could not exist. Protons and neutrons had not yet formed. Electrons drifted free. The universe was a seething, roiling plasma of pure energy, denser than anything our minds can comprehend. And then it expanded. This expansion was not like an explosion of matter into an empty space. There was no empty space for it to expand into. Space itself was stretching. Every point in the universe moving away from every other point, like dots drawn on the surface of a balloon being inflated. As the universe expanded, it cooled. As it cooled, particles began to form. Protons and neutrons came together. Atoms began to take shape. And approximately 380,000 years after the Big Bang, something remarkable happened. The universe cooled enough for electrons to bind to atomic nuclei, forming the first atoms. For the first time, the universe became transparent. Light could travel freely through it. That light, that first release of photons into a newly transparent universe, is the cosmic microwave background. It is the oldest light we can ever observe, because there is literally nothing older to observe. Everything before the CMB is hidden from us behind a wall of opacity, like trying to see through a thick fog. But the CMB itself is visible to us across the entire sky, and it carries within it the imprint of the universe as it was 380,000 years after creation. Every tiny temperature variation in the CMB tells us something about the structure of the early universe. It is a baby photograph of the cosmos, and scientists have studied it with extraordinary care and precision. The first full-sky map of the CMB was produced by the COBE satellite, launched in 1989. Scientists discovered that the CMB was almost perfectly uniform across the entire sky, with tiny temperature fluctuations at the level of 1 part in 100,000. These tiny fluctuations were exactly what the theory of cosmic inflation predicted. Inflation is the idea that in the very first moments after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, growing from something smaller than an atomic nucleus to something the size of a grapefruit in a tiny fraction of a second. This inflation smoothed out most variations in the early universe, but quantum fluctuations, tiny random variations at the subatomic level, were stretched to cosmic scales by the expansion. And these fluctuations eventually became the seeds of everything that exists today. Every galaxy, every star, every planet, every living thing. The WMAP satellite, which observed the CMB from 2001 to 2010, produced much more detailed maps. And it was in data from WMAP that the cold spot was first noticed by a group of scientists led by Kate Land and João Maguejo at Imperial College London, and confirmed more fully by researchers including Rongaram Cherry. In 2004, a team led by Vielva and colleagues published the first significant analysis of the cold spot, using data from the WMAP satellite. They found a region in the southern hemisphere of the CMB map, in the direction of the constellation Eridanus, that was statistically anomalous. Its temperature was lower than the surrounding area by an amount that standard cosmological models struggle to account for, and its size was larger than what you would expect from random chance. Later, the Planck satellite, operated by the European Space Agency and launched in 2009, produced the most detailed maps of the CMB ever made. And the cold spot was still there. Still anomalous. Still refusing to go away. The Planck data, published in a series of landmark papers between 2013 and 2015, confirmed that the cold spot was a real feature of the CMB, not an artifact of the instruments or a data processing error. It was real, and it was strange. So pause for a moment and ask yourself this question. If you had just discovered that there was a region of the universe so cold and so large that no current theory could fully explain it, what would you do? Would you assume it was a mistake? Would you wait for someone to come up with a boring, conventional explanation? Or would you feel that pull, that irresistible human urge to look deeper, to ask the bigger question? Because that is exactly what a growing number of scientists have done. And the answers they have found are not simple. They are not comfortable. They are, in some cases, almost terrifying in their implications. Let us start with the most conservative explanation, because even the conservative explanations for the cold spot are remarkable. One of the leading candidates is something called a supervoid. A supervoid is exactly what it sounds like: a vast region of space that contains significantly fewer galaxies, stars, and matter than the surrounding universe. The observable universe is structured in a way that cosmologists often compare to a cosmic web. Matter is distributed in an intricate network of filaments and sheets, with galaxy clusters concentrated at the nodes where these filaments intersect, and vast voids between them. These voids are not completely empty. They contain some galaxies, some gas, some dark matter, but they are far less densely populated than the filaments and clusters. Now, when photons from the CMB travel through space toward us, they can interact with large-scale structures in a phenomenon called the integrated Sachs-Wolf effect, or ISW effect. The basic idea is this: when a photon enters a region of space that contains a large amount of mass, it falls into the gravitational well of that mass and gains energy. As it climbs out on the other side, it loses energy. In a universe that is not accelerating in its expansion, these two effects cancel each other out, and the photon emerges with the same energy it had going in. But in a universe dominated by dark energy, which causes the expansion of space to accelerate, the gravitational wells of large structures are actually becoming shallower over time. So when a photon enters a gravitational well and then climbs out, the well has become a little shallower during the time it spent inside, and the photon ends up losing slightly less energy than it gained. This means it emerges with slightly more energy, slightly bluer, slightly hotter. The reverse is also possible. If a photon travels through a vast void, a region with less mass than average, the gravitational hills and valleys are inverted. The photon gains a little less energy than it would otherwise, and emerges slightly colder. This is one mechanism by which a supervoid could create the appearance of a cold spot in the CMB. In 2015, a team of researchers led by Istvan Saputty at the University of Hawaii announced that they had found evidence for a supervoid in the direction of the CMB cold spot. Using data from the Pan-STAR survey and the Wide Field Infrared Survey Explorer, they identified what appeared to be an enormous underdense region of space, approximately 1.8 billion light-years across, centered roughly 3 billion light-years from Earth, in the direction of the cold spot. This was extraordinary. A void of this size would be among the largest structures ever identified in the observable universe. And its location, pointing directly toward the cold spot, seemed too precise to be a coincidence. But here is where things get complicated. And this is where the story of the cold spot becomes something more than just a puzzle in astrophysics. It becomes a mystery that touches on the deepest questions about what the universe is, what it is made of, and whether our universe is all there is. When scientists calculated how much of the CMB temperature deficit in the cold spot could be explained by the ISW effect of the supervoid, they ran into a problem. The void could account for some of the temperature anomaly, but not all of it. Not even close to all of it. The supervoid, enormous as it was, could explain perhaps 20 to 50% of the temperature drop observed in the cold spot, depending on the assumptions you made about the void's density profile and the cosmological model you used. But it could not explain the rest. There was still a significant portion of the cold spot's anomalous temperature that remained unexplained. And this is where the hypotheses began to get more adventurous. There are, broadly speaking, several categories of explanation that have been proposed for the cold spot. The first is that it is a statistical fluke, a random fluctuation in a universe so vast that truly extraordinary things can happen by chance. The second is the supervoid hypothesis, which we have already discussed. The third involves modifications to the standard cosmological model, such as different assumptions about dark energy, the geometry of the universe, or the process of inflation. And the fourth, the most radical and the most intriguing, is that the cold spot is evidence of a collision between our universe and another universe in a larger multiverse. Let us spend some time with that last idea, because it deserves far more than a passing mention. The concept of a multiverse is not a fringe idea. It is not the province of science fiction writers and conspiracy theorists. It emerges naturally and independently from several of the most well-tested and well-established theories in modern physics. There are, in fact, multiple different versions of the multiverse hypothesis, each arising from different theoretical frameworks. One version arises from eternal inflation. If cosmic inflation is correct, and there is strong evidence that it is, then the inflationary process may not have stopped uniformly everywhere. In some regions, inflation continues indefinitely, creating new regions of space-time that expand away from each other faster than light can travel between them. These separate regions become causally disconnected from each other. They are, for all practical purposes, separate universes. Each one may have slightly different physical laws, different fundamental constants, different amounts of matter and energy. Together, they form an eternally inflating sea of bubble universes, each born when inflation ends in a local region and a new universe nucleates, like a bubble forming in boiling water. This is the idea at the heart of what physicists call the inflationary multiverse, or the eternal inflation scenario. And it has a remarkable implication. If our universe is one bubble in this larger inflationary sea, and if other bubbles exist, then it is possible that two bubbles could have collided during the early history of the universe. The collision would have released an enormous amount of energy and left behind a distinctive imprint in the CMB, a circular region where the temperature would be either higher or lower than the surrounding area, depending on the specifics of the collision. In 2007, two physicists named Ben Freevogel and Matthew Kleben, along with colleagues, published a paper analyzing what such a bubble collision would look like in the CMB. They showed that a collision with another bubble universe would produce exactly the kind of circular temperature anomaly that we observe in the cold spot. The anomaly would be roughly circular, it would have a specific temperature profile, and it would be located at one particular point on the sky rather than being distributed uniformly. They even made specific predictions about what additional features should accompany a bubble collision signature, such as polarization patterns in the CMB. And then, in subsequent years, other researchers began to look at the cold spot with these predictions in mind. And the more they looked, the more intriguing the match appeared. Ask yourself this. If you were a scientist who had spent years looking at maps of the earliest light in the universe, and you found a feature that matched the theoretical predictions of a bubble universe collision, what would you feel? Excitement, certainly, but also, perhaps, something close to vertigo. Because what you would be looking at, if the hypothesis were correct, would not just be a discovery. It would be the most important discovery in the history of human knowledge. It would be proof that our universe is not unique, that there are others. That reality, whatever that word means, is far larger and far stranger than we had ever imagined. The implications of that possibility are staggering. If there are other universes, they might have different physical laws. In some, gravity might be stronger. In others, the speed of light might be different. In some, the conditions that allowed stars and planets and life to form might never arise. In others, those conditions might be even more favorable than in ours, giving rise to forms of complexity and intelligence we cannot begin to imagine. The multiverse hypothesis, if true, would force us to completely rethink our understanding of why the universe is the way it is. The specific values of the constants of nature, the strength of gravity, the mass of the electron, the cosmological constant, would no longer need to be explained by some deep underlying theory. They would simply be the values that happen to arise in our particular bubble, one among an uncountable multitude. This idea is deeply unsettling to many physicists, because it seems to undercut the entire project of finding a single unified theory of everything. If different bubbles can have different physical laws, then there is no single set of laws to discover. The laws of physics are not written into the fabric of reality. They are accidents of our particular cosmic birth, no more fundamental than the specific shape of the snowflake that happened to fall on your doorstep one winter morning. But others find the multiverse strangely liberating. It answers one of the deepest questions in all of science. Why does the universe have the specific properties that allow life to exist? The answer, in the multiverse framework, is the anthropic principle. We observe the universe we observe because we can only exist in a universe that is compatible with our existence. We are not here despite the seemingly unlikely values of the physical constants. We are here because of them. And in a large enough multiverse, some bubbles will inevitably have the right properties. We find ourselves in one of those bubbles not because of any grand cosmic plan, but because no other kind of universe could contain observers to notice anything at all. This is a profound and somewhat dizzying idea. And the cold spot sits right at the center of it, a possible fingerprint of another universe, pressing against our own. But before we get too carried away with the romance of parallel universes, we need to be honest about the limitations of what we currently know. Science is not a collection of exciting ideas. It is a process of testing those ideas against reality. And the cold spot, as fascinating as it is, has not yet been definitively explained. The statistical significance of the cold spot is a matter of ongoing debate. When the Planck team analyzed the CMB data in their 2013 papers, they found that the cold spot was indeed anomalous, but they were careful about how they expressed this. The significance of any anomaly in the CMB depends heavily on how you define what you are looking for and how many independent tests you perform. This is a well-known problem in statistics, sometimes called the look elsewhere effect or the problem of a posteriori statistics. If you look at a dataset for long enough and test enough hypotheses, you will eventually find patterns that appear significant but are actually just random coincidences. However, the cold spot is not just a statistical blip. It has a specific, well-defined location. It has been confirmed by multiple independent analyses using data from multiple independent satellites. It has a temperature profile and a size that are consistent across different measurements. And the probability that it arose by chance, even accounting for the look elsewhere effect, is low enough that it demands an explanation. The question is, what explanation? Researchers have been working on this for 2 decades now, and the answer is still not clear. Every proposed explanation has problems. The statistical fluke explanation is possible but feels intellectually unsatisfying, a bit like explaining a mysterious event by saying it just happened. The supervoid explanation is observationally supported but quantitatively insufficient. The modifications to cosmology explanations are mathematically sophisticated but lack additional observational support. And the bubble collision hypothesis is theoretically compelling but extraordinarily difficult to test. This is the nature of the frontier of science. Not clean answers wrapped in neat packages, but deep questions sitting in the middle of incomplete knowledge, surrounded by the flickering light of hypotheses and the steady, patient work of researchers trying to understand. And the people who have devoted their careers to understanding the cold spot are remarkable individuals. They are not just abstract thinkers in ivory towers. They are human beings who wake up every morning burning with curiosity about the most fundamental questions that any mind has ever asked. What is the universe? Where did it come from? Is it all there is? And they bring to these questions not just intellect but something that looks very much like wonder. Consider for a moment what it must be like to be a cosmologist working on the CMB. You are working with data from instruments sensitive enough to measure temperature differences of a millionth of a degree across the entire sky. You are building maps of a phenomenon that occurred 13.8 billion years ago, at a distance so great that the light carrying information about it has been traveling through expanding space for longer than the Earth has existed. And you are doing this in the hope that hidden within those maps are clues not just to how the universe formed, but to whether our universe is part of a larger structure, whether there is something beyond the horizon of the observable cosmos. There is something almost mystical about it, even though every step of the process is rigorously scientific. The gap between the instruments we use and the phenomena we are studying is so enormous, the patience required so extraordinary, that the work takes on a quality of devotion that goes beyond ordinary intellectual inquiry. The cold spot has attracted attention not just from cosmologists, but from physicists working in string theory, quantum gravity, and the foundations of quantum mechanics. Each of these fields has its own version of the multiverse hypothesis, and each of them finds in the cold spot a potential connection to their deepest theoretical questions. In string theory, the landscape of possible universes is estimated to be almost incomprehensibly vast, with something like 10 raised to the power of 500 different possible vacuum states, each corresponding to a different set of physical laws. The theory predicts that different regions of the eternal inflation landscape would settle into different vacuum states, producing bubble universes with radically different properties. The cold spot, in this context, might be a window onto the string theory landscape, a hint that the vast theoretical machinery of string theory is not just mathematics but describes something genuinely real. In quantum mechanics, particularly in the many-worlds interpretation developed by Hugh Everett in 1957, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. These branches do not interact with each other in any way that current physics can detect, and they do not produce the kind of large-scale collision signature that the bubble universe hypothesis predicts. But they do raise similar questions about the nature and multiplicity of reality. The cold spot is not usually considered evidence for the many-worlds interpretation specifically, but the existence of multiple interpretations of quantum mechanics, several of which involve multiple realities, adds to the intellectual climate in which the cold spot becomes especially interesting. Now let us go deeper into the actual physics of what a bubble universe collision would look like, because it is worth understanding this in some detail. When two bubble universes collide, they are not colliding in the ordinary sense of two objects crashing into each other. They are regions of space-time that, from an inside perspective, are infinite in extent. The collision is better described as one bubble nucleating within the false vacuum that surrounds another bubble and then expanding. The boundary between the two bubbles is a domain wall, a thin shell where the properties of space-time transition abruptly from one vacuum state to another. When two such bubbles collide, the collision produces a wave that propagates through each bubble, carrying energy from the collision event. In our bubble, this wave would appear as a disturbance in the CMB, arriving from the direction of the collision. The disturbance would be confined to a circular region of the sky, bounded by the geometry of how the collision wave intersects our surface of last scattering, which is the technical name for the moment when the CMB was formed. The temperature within this circular region could be either higher or lower than the surrounding CMB, depending on the specifics of the collision, which vacuum state the colliding bubble was in, how much energy was released, and the exact geometry of the collision. Rangaram Cherry, a researcher at the California Institute of Technology, published a paper in 2015 that reignited interest in the cold spot as a potential evidence of a bubble collision. He found what he believed might be a signal in the CMB, a region of slightly elevated temperature in a location consistent with a polarized light expected from a bubble collision, though he was careful to note that the probability of the signal being real was only about 1 in 50, not enough to constitute a firm detection. His paper was peer-reviewed and published in the Astrophysical Journal, and while many of his colleagues were skeptical, none dismissed it outright. This is how science works at the frontier. Not with dramatic announcements and definitive proofs, but with tentative signals and careful statistics and arguments about interpretation. Progress is made incrementally, each paper adding a piece to a puzzle whose full picture may not be visible for decades. And it is worth asking, would we even recognize a bubble collision signature if we saw one? The theoretical predictions for what such a signature should look like depend on assumptions about the properties of the colliding bubble, assumptions that we have no independent way to verify. This is one of the deep challenges in testing multiverse theories. The theory is so flexible, with so many possible configurations of bubble universes, that it can potentially explain almost any observation. This is both its strength and its weakness. A theory that can explain everything explains nothing, in the sense that it makes no specific predictions that could falsify it. Some physicists, notably David Weinberg and others who have written about the philosophy of multiverse theories, have argued that the multiverse hypothesis is not science at all in the traditional sense, because it cannot be falsified. If we see the cold spot, it might be a bubble collision. If we do not see any anomalies in the CMB, it is still consistent with a multiverse, because most bubble collisions might produce signatures too subtle to detect. The multiverse theory, in this view, explains everything in principle and nothing in practice. This is a deep criticism, and it deserves to be taken seriously. But others have pushed back. Researchers like Matthew Kleben, Anthony Aguirre, and Sarah Shandera have argued that bubble collision signatures are not just a post hoc explanation for any anomaly. They make specific, quantitative predictions about the properties of any collision signature. Its geometry should be circular, its temperature profile should have a specific shape, and it should be accompanied by distinctive polarization patterns in the CMB. These are predictions that can be tested. And if the cold spot were explained by a bubble collision, it would need to match all of these predictions, not just the temperature anomaly. So the question is not merely whether the cold spot exists, which it does, but whether its detailed properties match the theoretical predictions of a bubble collision. And this is where future observations become crucial. The next generation of CMB experiments could provide definitive answers. The Simons Observatory in Chile, the CMB S4 experiment, and future space-based missions will produce maps of the CMB polarization with unprecedented sensitivity. If the cold spot is caused by a bubble universe collision, these maps should reveal specific polarization signatures around the cold spot that match theoretical predictions. If no such signatures are found, the bubble collision hypothesis will be significantly weakened, though not definitively ruled out, because the absence of a detected signal might simply mean the collision was too weak or the geometry was unfavorable. If the signatures are found, however, it will be arguably the most significant scientific discovery in human history. That is not hyperbole. Proof that our universe had collided with another universe, proof that there are other universes beyond our own, would fundamentally change our understanding of what reality is. It would be a revolution that makes the Copernican revolution, the shift from an Earth-centered to a Sun-centered model of the solar system, look like a minor editorial correction. It would not just expand our picture of the universe. It would shatter the frame entirely and force us to rebuild it from the ground up. And yet, even if the bubble collision hypothesis is not confirmed, the cold spot will remain a fascinating and important feature of the CMB, because its existence raises questions that go beyond any single explanation. It raises questions about the limits of our standard cosmological model, about the nature of the universe's geometry and topology, about the distribution of matter on the largest scales, and about the accuracy of our understanding of cosmic inflation. Let us spend some time on one of these alternative directions, because the geometry and topology of the universe is a subject that is almost as mind-bending as the multiverse. The standard cosmological model assumes that the universe is, on the largest scales, geometrically flat. This means that parallel lines never converge or diverge, that the angles of a triangle always add up to 180 degrees, that the geometry of space follows the rules you learned in high school. But is the universe actually flat? The observations of the CMB suggest that it is flat to within the limits of what we can measure, but that does not mean it is perfectly flat. There could be small deviations from flatness that our current observations are not sensitive enough to detect. Moreover, flatness tells us about the curvature of space but not about its global topology. A space can be flat and still have a finite size, connected in ways that create unexpected structures. Imagine a torus, the shape of a donut. The surface of a torus is geometrically flat in the sense that parallel lines on it do not converge or diverge if you look at a small enough region. But the global structure of the torus is connected in a way that means if you travel far enough in one direction, you come back to where you started. Could the universe have a topology like this? Could it be, in some sense, finite and self-connected in ways we have not yet detected? Some researchers have speculated that the cold spot could be related to the topology of the universe, a region where the CMB photons have traveled around the universe more than once and interfered with themselves in a way that produces an anomalously cold or hot region. This is a speculative idea, and the observational evidence for it is not strong. But it illustrates the extraordinary range of possibilities that the cold spot opens up. The universe we see is about 93 billion light-years in diameter, which is larger than the 13.8 billion light-years you might expect from the age of the universe, because space itself has been expanding since the Big Bang. Beyond that 93 billion light-year sphere is more universe, But we cannot observe it because the light from those regions has not had enough time to reach us. We are, in a sense, trapped inside a cosmic horizon. Everything beyond that horizon is forever inaccessible to direct observation. But the physics happening beyond our horizon is not necessarily the same as the physics inside it. If the universe is infinite, which is one possibility consistent with the observations, then by sheer statistics, there must be regions of the universe so far away that they are effectively independent of ours. In an infinite universe with random initial conditions, every possible configuration of matter and energy will eventually occur somewhere. This is a form of multiverse that requires no exotic new physics, just the logical implications of an infinite universe with random variations. And in such a universe, extreme configurations would exist. Regions that are vastly colder than average. Regions that are vastly hotter. Regions where matter is distributed in ways that look statistically impossible from within any single horizon. The cold spot could simply be a glimpse of such an extreme region, visible to us because it happens to lie just inside our cosmic horizon, close enough for its photons to reach us. This explanation has the appeal of requiring no new physics. It works within the standard cosmological model, the lambda CDM model, which describes the universe in terms of dark energy, dark matter, and ordinary matter. Lambda CDM has been enormously successful. It describes the large-scale structure of the universe, the distribution of galaxies, the expansion history, and the properties of the CMB with remarkable accuracy. And it allows for large temperature fluctuations, even very large ones, as rare but possible events. But the question is, how rare? And can we ever know whether an event in the universe is truly a rare fluctuation or evidence of something more fundamental? This is where the philosophy of science gets entangled with the practice of science. The cold spot sits right at the intersection of what is measurable and what is merely possible. It is real enough to detect, but strange enough to resist explanation. It is precise enough to generate specific hypotheses, but ambiguous enough to keep every hypothesis alive. It is, in short, exactly the kind of anomaly that drives science forward. And the scientists driving it forward are not just a faceless collective. They are individual human beings with names and stories and moments of personal revelation. There is something deeply human about the search for the origin of the cold spot, a search that has consumed careers and prompted fierce debates and led to some of the most creative theoretical work in modern cosmology. Laura Mersini-Houghton is one of the most prominent scientists associated with the bubble collision hypothesis for the cold spot. A theoretical physicist at the University of North Carolina at Chapel Hill, she has argued not just that the cold spot could be evidence of a bubble collision, but that it was predicted by her theoretical framework before it was confirmed as an anomaly. Her theoretical model, which she has called the landscape multiverse theory, makes specific predictions about what kinds of imprints neighboring bubble universes would leave on our CMB. In 2006, before the full extent of the cold spot anomaly was appreciated by the broader community, Mersini-Houghton and Richard Holman published a paper arguing that quantum entanglement between our universe and neighboring bubble universes during inflation would leave distinctive cold regions in the CMB. The cold spot, she argued, was exactly the kind of feature her theory predicted. This is a bold claim, and it has been met with both enthusiasm and skepticism. The enthusiasm comes from the fact that she made the prediction before the confirmation of the anomaly. The skepticism comes from questions about whether her theoretical framework is sufficiently rigorous and specific to constitute a genuine prediction. The debate around Mersini-Houghton's work reflects a broader tension in modern theoretical physics between mathematical creativity and empirical rigor. String theory, loop quantum gravity, eternal inflation, and related frameworks are all extraordinarily mathematically rich. They generate vast landscapes of possible predictions. But the challenge of connecting these theoretical landscapes to observable data is enormous. The cold spot is one of the few places where that connection might be made. And for that reason, it is fiercely contested territory. Sarah Shandera and her collaborators have done careful statistical work trying to assess whether the cold spot's properties are consistent with a bubble collision. They have found that the detailed shape of the cold spot, including the temperature profile across it and the way its edges are defined, is broadly consistent with what a bubble collision would produce. But they have also found that the consistency is not perfect, and that the statistical significance is not high enough to constitute a detection. This is where we are today. The cold spot remains unexplained. The supervoid is real but insufficient. The bubble collision is theoretically compelling but unproven. The standard cosmological model is under stress but not broken. And the next generation of observations is still in preparation, not yet capable of delivering the definitive answers that everyone is waiting for. In the meantime, the cold spot sits in the southern sky, in the direction of the constellation Eridanus, a few degrees below and to the right of the bright star Epsilon Eridani, which happens to be one of the nearest sun-like stars to our solar system. And every time the world's best telescopes and satellites scan that region of the sky, they see the same thing. A circular region of slightly lower temperature, surrounded by a ring of slightly higher temperature, embedded in the otherwise remarkably uniform glow of the cosmic microwave background. It is a subtle feature. If you were to look at a map of the CMB, you would see it as a faint blue patch against the predominantly green background of the standard CMB temperature map. It does not jump out at you. It does not announce itself with drama or fanfare. But once you know it is there, once you know what it might mean, it becomes impossible to look at the rest of the universe in quite the same way. Because the cold spot is not just a cosmological anomaly. It is a question. The deepest kind of question. Not just what caused this temperature anomaly, but what is the universe? Are there others? And if there are, what does it mean to be one universe among many? These questions connect to something fundamental in human psychology. We have always looked at the sky and asked, are we alone? Are we special? Is there something beyond the horizon of what we can see? The cold spot transforms these ancient, almost spiritual questions into the domain of rigorous science. It is a place where the infinite vastness of the cosmos presses against the limits of what we can know, and where the tools we have built are almost, but not quite, sufficient to pierce the veil. There is another dimension to the cold spot that deserves exploration, and that is what it tells us about the nature of voids in the universe. Even if the supervoid explanation turns out to be the correct one, the void itself is a remarkable structure. A region 1.8 billion light-years across, containing far less matter than the surrounding universe, is not just a curiosity. It is a window into the large-scale structure of the cosmos and the processes that shaped it. The universe we see today, with its web of filaments and voids and clusters, is the result of 13.8 billion years of gravitational evolution starting from the nearly smooth conditions of the early universe. Small overdensities in the early universe, regions where matter was slightly more concentrated than average, grew over time as gravity pulled more and more matter toward them. Simultaneously, regions that were slightly underdense became even more underdense as matter was pulled away from them into the surrounding overdensities. This process, called gravitational instability, is responsible for all of the large-scale structure we observe today. The voids are, in a sense, the negative spaces of this cosmic sculpture. They are the regions that were emptied out over cosmic time as the surrounding matter condensed into filaments and clusters. And they are not static. Voids grow over time, becoming larger and emptier as the expansion of the universe accelerates. Dark energy, the mysterious force driving the acceleration, plays a crucial role in the evolution of voids. In a universe with more dark energy, voids would be larger and emptier. In a universe with less dark energy, they would be smaller. The supervoid associated with the cold spot, if it is real and has the properties estimated by Sepudi and colleagues, is larger than what the standard cosmological model predicts should be possible at very high confidence. Some analyses have suggested that a void of this size and depth is a 1 in 10,000 year event within the standard model, a statistical extreme that would be expected to occur by chance somewhere in the observable universe, but that we would not normally expect to find pointed directly at one of the most prominent anomalies in the CMB. This coincidence, a supervoid that is itself anomalously large pointing toward a CMB anomaly that is itself anomalously cold, is suggestive. Either it is a remarkable coincidence, or there is something about the cold spot region that promotes the formation of large voids, or both the CMB anomaly and the supervoid are being caused by a third factor that we have not yet identified. What could that third factor be? This is one of the most fertile areas of theoretical speculation around the cold spot. Some researchers have proposed that the cold spot region might be associated with a large-scale streaming flow, a coherent bulk motion of matter on enormous scales that the standard model does not fully predict. Others have suggested it might be related to the so-called axis of evil, another large-scale anomaly in the CMB in which the largest scale temperature variations seem to be aligned in an unexpected way with the plane of the solar system, suggesting a mysterious preferred direction in the universe that should not exist if the universe is truly isotropic and homogeneous on the largest scales. The possibility that multiple CMB anomalies might be related to each other is exciting but also dangerous from a scientific standpoint. It is tempting to weave different anomalies together into a single grand narrative, but without strong theoretical guidance, this can become a form of motivated reasoning, finding patterns that feel significant but are actually the result of looking at complex data with a human mind that is exquisitely tuned to find patterns even where none exist. Ask yourself this question. If you were shown a random collection of dots on a sheet of paper and told that some of them might form a meaningful pattern, how long would it take before you started seeing patterns? Our brains are pattern recognition machines, evolved over millions of years to find order in chaos, because for our ancestors, the cost of missing a real pattern, like the shadow of a predator in the grass, was catastrophic, while the cost of seeing a false pattern was merely embarrassment. This evolutionary inheritance serves us poorly in cosmology, where the patterns we are looking for are subtle, the data is noisy, and the hypotheses we bring to the data can color what we see. This is why statistical rigor is so important in cosmology, and why the debates about the significance of the cold spot and related anomalies are so intense. When the Planck team reported on anomalies in the CMB in 2015, they were careful to present their results in a framework that accounted for the number of different tests they had performed. They found that the cold spot was anomalous at a level of about 2 to 3 sigma in different analyses. This means that if the universe were described perfectly by the standard cosmological model, you would expect a feature like the cold spot to arise by chance in perhaps 1 in 20 to 1 in 1,000 universes, depending on how you define the test. That is not nothing, but it is also not the 5 sigma threshold that particle physicists use to declare a discovery. Yet 2 to 3 sigma anomalies do not go away on their own. They either get explained, or they get stronger as more data comes in, or they get weaker and disappear. The cold spot has been in the 2 to 3 sigma range for 2 decades. It has not disappeared, and the question of whether it will get stronger or weaker as future observations become available is one of the most important open questions in modern cosmology. Future CMB experiments are planning to measure the polarization of the CMB with much greater precision than any previous mission. The reason this matters is that polarization carries complementary information to temperature. The CMB is not just a map of temperature, it is also a map of the polarization of the ancient light. This polarization was generated by the same physical processes that created the temperature variations, but it provides a different view of them. Certain features in the temperature map should have specific associated polarization patterns, and comparing the temperature and polarization data provides a much more powerful test of any hypothesis than temperature alone. For the bubble collision hypothesis specifically, a collision would produce a characteristic polarization pattern around the cold spot, a pattern of E-mode polarization that would be concentrated near the edge of the cold region. If future experiments detect this specific polarization signature in exactly the right location and with the right amplitude, the case for a bubble collision would become enormously stronger. If they detect nothing, the hypothesis will be difficult to sustain. This is the razor's edge on which the most extraordinary possible discovery in the history of science currently balances. On one side, the boring but safe explanation, statistical fluctuation, supervoid, or some modification to cosmology. On the other side, the breathtaking but uncertain explanation, another universe, pressing against our own, leaving its mark on the oldest light in the cosmos. While we wait for those future observations, let us take a moment to consider the human context of this search. Science is often presented as a cold, impersonal process of hypothesis and testing, divorced from emotion and human experience. But that is not what it looks like from the inside. The scientists who work on the CMB and the cold spot are passionate, sometimes fiercely competitive, and driven by a sense of wonder and urgency that is anything but cold. The history of CMB cosmology is filled with stories of intellectual conflict and dramatic discovery. The story of how the CMB was first discovered is one of the great accidental discoveries in the history of science. In 1964, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna to try to make precise measurements of radio signals from the Milky Way. They found a persistent, annoying background noise in their instrument that they could not eliminate no matter what they did. They checked the antenna for faults. They recalibrated everything. They even physically cleaned the antenna, removing pigeons that had been nesting in it and scrubbing away what they diplomatically described as a white dielectric material. But the noise persisted. At the same time, a group of theoretical physicists at Princeton University, led by Robert Dick and including Jim Peebles, were working on the theoretical prediction that if the Big Bang Theory were correct, there should be a remnant glow of microwave radiation filling the universe. They were even building an instrument to try to detect it. When someone connected the two groups, it quickly became clear that Penzias and Wilson had already found what the Princeton group was looking for. They had been trying to get rid of the most important signal in the history of cosmology. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. This story reminds us that science at its best is surprising. The most important discoveries are often not the ones you were looking for. And the cold spot has that quality. No one planned to find it. No one predicted its specific location or properties. It emerged from the data, stubborn and unexplained, demanding attention. The same quality of unexpected discovery characterizes the history of dark matter and dark energy, two of the most important discoveries in modern cosmology. Dark matter was first postulated by Fritz Zwicky in the 1930s to explain why the galaxies in the Coma cluster were moving too fast to be held together by the visible matter alone. Decades later, Vera Rubin's precise measurements of galaxy rotation curves provided incontrovertible evidence that most of the mass in galaxies is invisible. Today, dark matter is estimated to make up about 27% of the total energy content of the universe, while ordinary matter, everything we can see, accounts for only about 5%. Dark energy is even stranger. In 1998, two independent teams studying distant supernovae discovered that the expansion of the universe was not slowing down, as it should be if gravity were the dominant force on large scales. It was accelerating. Something was pushing the universe apart. This something, called dark energy, makes up approximately 68% of the total energy content of the universe. We have no idea what it is. We know only that it acts like a negative pressure, counteracting gravity and causing space to expand at an increasing rate. Together, dark matter and dark energy make up about 95% of the total energy content of the universe. The stuff we are made of, the stuff we can see and touch and measure directly, is a tiny fraction of what actually exists. We live in a universe that is overwhelmingly made of things we do not understand. Against this backdrop, the cold spot does not seem quite so isolated in its strangeness. It is one among many profound mysteries in modern cosmology, all pointing toward the same conclusion. We have learned an enormous amount about the universe in the last century, but we are still in the early chapters of understanding it. The cold spot's relationship to dark energy is particularly interesting. The integrated Sachs-Wolf effect, which we discussed in connection with the supervoid, is a direct probe of dark energy. In a universe without dark energy, the effect would not occur, or would be much weaker. The fact that we can see ISW effects at all is evidence for the existence of dark energy. And the supervoid in the direction of the cold spot, if it is real, provides one of the most dramatic ISW signals ever potentially detected. This means that studying the cold spot could teach us not just about the cold spot itself, but about the nature of dark energy, one of the deepest mysteries in all of physics. Dark energy is often described as the cosmological constant, a term that Einstein introduced into his equations of general relativity in 1917 to prevent the universe from collapsing under gravity. At the time, the universe was thought to be static, and Einstein added the cosmological constant as a kind of anti-gravity term to maintain the static state. When Hubble discovered that the universe was expanding in 1929, Einstein reportedly called the cosmological constant his greatest blunder. But when dark energy was discovered in 1998, it turned out that Einstein's greatest blunder was actually correct. The universe does have a cosmological constant, or something that behaves exactly like one. But why does the cosmological constant have the value it has? This is one of the deepest unsolved problems in theoretical physics, known as the cosmological constant problem. If you try to calculate the value of the cosmological constant from first principles using quantum field theory, you get a number that is vastly larger than the observed value, by a factor of something like 10 raised to the power of 120. This enormous discrepancy, the largest discrepancy between theory and observation in the history of science, suggests that something is deeply wrong with our understanding of either quantum field theory, gravity, or the relationship between them. One proposed solution to the cosmological constant problem involves the multiverse. In the eternal inflation picture, different bubble universes can have different values of the cosmological constant. A universe with a cosmological constant much larger than ours would expand too rapidly for galaxies and stars to form. A universe with a negative cosmological constant would collapse back on itself before life could evolve. Only universes with a cosmological constant in a narrow range, comparable to the observed value, would be capable of supporting complexity and observers. This is the anthropic argument for the cosmological constant, and it was actually made before dark energy was discovered. Steven Weinberg, one of the architects of the Standard Model of particle physics, made this prediction in 1987. The discovery of dark energy in 1998, with a value close to what the anthropic argument suggested, was a remarkable vindication of this line of reasoning. The multiverse thus provides a possible solution to not one but two of the deepest problems in modern physics: the cosmological constant problem and the fine-tuning of the other constants of nature. And the cold spot, if it is evidence of a bubble collision, would be direct observational support for the multiverse framework in which these solutions are embedded. This is why the cold spot matters so much. It is not just an interesting anomaly in a satellite dataset. It is a potential window onto a set of ideas that could resolve some of the most fundamental puzzles in all of science. And if those ideas are correct, they would represent not just a revolution in cosmology, but a transformation in our understanding of what science is capable of knowing and what it means for the universe to exist at all. Let us now try to paint a more vivid picture of what the cold spot actually looks like in the context of the CMB map, because understanding this visually is crucial to appreciating its significance. Imagine a map of the entire sky, folded out flat like a Mercator projection of the Earth. The colors on this map represent the temperature of the CMB at every point in the sky. The average temperature of the CMB is about 2.725 Kelvin, which is just above absolute zero, the coldest temperature possible. Variations from this average are tiny, just a few hundred thousandths of a degree, but they are visible in false color maps that use colors ranging from deep red for the hottest regions through yellow, green, and blue to deep purple or dark blue for the coldest regions. In this map, most of the variation is in the form of a complex, modeled pattern of warm and cold spots, roughly the same on all scales, looking somewhat like the surface of a distant planet seen through a slightly blurry telescope. There is no single dominant feature. The pattern is statistically isotropic, meaning it looks the same in every direction, consistent with the idea that the early universe was the same everywhere and expanding equally in all directions. And then there is the cold spot. It sits in the southern hemisphere of the CMB map, roughly centered around coordinates that correspond to the direction of the constellation Eridanus. In the false color maps produced by the WMAP and Planck satellites, it appears as a dark blue or dark purple patch, surrounded by a ring of slightly elevated temperature that appears yellow or orange in contrast to the green background. It is not dramatically obvious in the full sky map. You need to know where to look. But once you see it, And once you know what it means, it draws the eye in a way that is hard to explain. There is something uncanny about it. A circular, cold region in the ancient light of creation, perfectly placed to be seen by creatures who evolved billions of years later on a small planet orbiting an ordinary star, asking what it is and where it came from. If you looked at the CMB map on a computer screen and traced a circle around the cold spot with your finger, you would be encompassing an area of the sky that, on the surface of last scattering 13.8 billion light-years away, corresponds to a physical region roughly 600 to 900 million light-years across. That is an almost incomprehensible size. The entire observable universe is only about 93 billion light-years in diameter. The cold spot region encompasses roughly 1% of the observable universe's total volume, all of it slightly cooler than it should be. To put this in even more human terms, the Milky Way galaxy is about 100,000 light-years across. The cold spot region is about 10,000 times wider than our entire galaxy. If you were a cosmic being able to see the structure of the universe on the largest scales, looking from a distance at the surface of last scattering, the cold spot would be a noticeable feature. A blemish. A whisper of something different in the otherwise smooth fabric of the ancient sky. The mystery of the cold spot is not just about its temperature or its size. It is also about its shape. The cold spot has an approximately circular boundary, which is significant. Random temperature fluctuations in the CMB do not generally produce perfectly circular features. They tend to produce irregular, complex patterns with no preferred shape. A circular feature suggests either a physical process with circular symmetry, like a spherical void or a circular wave from a collision, or a very unusual random fluctuation that happened to be circular. Researchers who have studied the detailed shape of the cold spot have found that it is not perfectly circular, but it is more circular than would be expected from a random fluctuation. This is consistent with both the supervoid hypothesis, because a spherical void would produce a roughly circular temperature depression, and the bubble collision hypothesis, because the intersection of a spherical collision wave with our surface of last scattering would produce a circular boundary. The circularity of the cold spot has also led to speculation about completely different physical processes. Some researchers have proposed that the cold spot could be related to a cosmic texture, a topological defect in the fabric of spacetime left over from a phase transition in the early universe. In the very early universe, when the temperature was extraordinarily high, the fields that give particles their properties may have undergone phase transitions analogous to water freezing into ice. In these transitions, different regions of the universe could have settled into different states, like ice crystals forming in different orientations in a freezing pond. Where these regions meet, there would be boundaries where the field transitions rapidly from one state to another. These boundaries, called topological defects, can take the form of cosmic strings, domain walls, or textures, depending on the symmetry of the underlying field. A texture, specifically, is a type of topological defect that is not localized to a one-dimensional string or a two-dimensional wall but is distributed in 3 dimensions. When a texture collapses under its own self-interaction, it can release energy in a specific pattern, and this could leave a cold or hot spot in the CMB with a circular profile. Neil Turok and colleagues proposed this mechanism in the early 1990s, and it has been periodically revisited as an explanation for the cold spot. The texture hypothesis is interesting because it predicts a specific temperature profile for the cold spot. A temperature that decreases toward the center, a specific relationship between the depth and width of the cold region, and a particular polarization signature. Analyses of the Planck data suggest that the cold spot's temperature profile is broadly consistent with what a texture would produce, though the agreement is not perfect. Each of these hypotheses, the supervoid, the bubble collision, the texture, and others, make specific predictions that future observations will test. And this is what makes the cold spot such an extraordinary driver of scientific progress. It is not just a mystery, it is a constraint. Any successful theory of the universe must be able to explain it. And by requiring that explanation, the cold spot forces cosmologists to think harder, test deeper, and push the boundaries of what the universe is allowed to contain. Now let us turn to a broader question that the cold spot raises. one that goes beyond cosmology and touches on something deeply philosophical. What does it mean to live in a universe that contains such profound mysteries? We tend to think of our understanding of the universe as a story of progress, a march from ignorance to knowledge, from darkness to light. And in many ways, it is. We have come an extraordinary distance in the last century. We have mapped the entire observable universe. We have detected gravitational waves from colliding black holes. We have photographed a black hole directly. We have traced the evolution of the cosmos from the Big Bang to the present day. We have built a standard model of particle physics that describes the behavior of matter and energy with extraordinary precision. But the cold spot reminds us that the march of progress does not always lead to the certainty we expect. Sometimes it leads us to deeper uncertainty. Sometimes the better our instruments become, the more anomalies we find. Sometimes the closer we look, the stranger everything appears. This is not a failure of science. It is its greatest triumph. Every genuine mystery is an invitation to go further. Every anomaly is a doorway. And the cold spot is perhaps the most tantalizing doorway in all of modern science, because behind it might lie the answer to a question that human beings have been asking in different forms for as long as we have been capable of asking questions at all. Is there more to reality than what we can see? The universe we observe is the universe we evolved to observe. Our senses, our instruments, even our mathematical intuitions are adapted to the scales and conditions of the world in which we live. The universe on the largest scales is so far from our everyday experience that it is genuinely astonishing that we can understand any of it at all. The cold spot sits at the very edge of what we can observe and what we can understand, at the boundary between the known and the unknown, between the universe we inhabit and whatever might lie beyond. And it is at exactly this kind of boundary that the most profound discoveries in the history of science have always been made. Copernicus standing at the boundary between an Earth-centered and a Sun-centered cosmos. Newton standing at the boundary between everyday mechanics and the mathematics of gravity. Einstein standing at the boundary between Newtonian physics and the curved spacetime of general relativity. Planck, Bohr, Heisenberg, and the other quantum pioneers standing at the boundary between the familiar classical world and the utterly alien quantum realm. The cold spot might be the next boundary. The one between the universe and the multiverse. The one between the cosmos we know and the vast, incomprehensible landscape of all that is. Or it might not be. It might turn out to have a mundane explanation, a statistical fluke made significant by our pattern-seeking minds, or a supervoid slightly larger than expected but within the allowed range of the standard model. And if that is the answer, then the cold spot will fade from the headlines but not from the textbooks, because even a large supervoid is a remarkable structure, and even a statistical anomaly tells us something about the limits of our models. But there is a possibility, still alive and vibrant, that the cold spot is something more, that it is a message from beyond the boundaries of our universe. Not a message in the sense of information deliberately sent, because whatever is on the other side of a bubble collision, if there is anything at all, cannot be communicating with us intentionally. But a message in the cosmic sense, a mark left by the collision of worlds, a scar in the ancient light, an echo of an event so vast and so ancient that its significance dwarfs everything our civilization has ever achieved or imagined. And if that is what it is, then we are very lucky indeed. Because the odds of that collision happening close enough to leave a detectable mark in our CMB, in precisely the right direction, at precisely the right angular scale, are not easy to estimate but are certainly very small. We might be living in one of the few bubble universes in the entire multiverse that has a neighboring universe close enough to touch. And the touch has left a mark that we, tiny creatures on a small planet in an ordinary galaxy, have somehow managed to find. There is something poetic about that. Something that transcends the purely scientific and touches on a kind of awe that is hard to articulate but impossible to deny. The universe is not indifferent to us in the way that people sometimes say. It is not cruel or kind. It is simply vast. And in its vastness, it has produced beings capable of asking questions about it. And in the process of asking those questions, we have found the cold spot. A feature so strange and so significant that it might, just might, be our first glimpse of something beyond everything we have ever known. This brings us to the question of what happens next. Because the story of the cold spot is not over. It is, in many ways, just beginning. The Simons Observatory, a ground-based CMB experiment located at an altitude of 5,000 meters in the Atacama Desert in Chile, began operations in 2023. It consists of multiple telescopes with thousands of detectors, designed to measure the CMB's temperature and polarization with sensitivity that surpasses any previous ground-based instrument. The Simons Observatory will produce detailed maps of a significant fraction of the sky, with enough sensitivity to detect subtle polarization signals around features like the cold spot. CMB S4, a next-generation ground-based CMB experiment currently in the planning and early construction phases, will go even further. With hundreds of thousands of detectors, it will be sensitive enough to detect even very subtle signatures in the CMB polarization. If a bubble collision left a polarization signature around the cold spot, CMB S4 should be able to detect it. If it is not there, the bubble collision hypothesis will face its most severe test. Space-based experiments are also on the horizon. Lightbird, a Japanese-led space mission planned for launch in the early 2030s, is designed primarily to detect the polarization signal from primordial gravitational waves generated during inflation. But it will also provide a full-sky polarization map with exquisite sensitivity, which will be invaluable for studying the cold spot and other CMB anomalies. PICO, a proposed NASA mission, would combine the full-sky coverage of a space mission with the sensitivity of the most advanced ground-based experiments. If approved and funded, it could provide the most comprehensive picture of the CMB ever assembled. Each of these experiments will bring us closer to an answer. Not just about the cold spot, but about the nature of inflation, the existence of primordial gravitational waves, the properties of dark energy, and the possible signatures of physics beyond our standard cosmological model. The next decade of CMB cosmology is going to be extraordinary. The combination of data from the Simons Observatory, CMB, S4, Lightbird, and other experiments will provide a level of detail about the CMB that was unimaginable even 20 years ago. And somewhere in that wealth of data, the answer to the mystery of the cold spot might finally reveal itself. But there is another kind of observation that could also shed light on the cold spot: galaxy surveys. The Large Synoptic Survey Telescope, now operating as the Vera C. Rubin Observatory in Chile, is mapping billions of galaxies across the observable universe. The Dark Energy Spectroscopic Instrument, or DESI, is measuring the spectra of tens of millions of galaxies to map the three-dimensional distribution of matter in the universe. The Euclid space mission, launched in 2023, is creating a 3D map of the universe extending out to several billion light-years. These surveys will allow astronomers to map the supervoid in the direction of the cold spot with far greater precision than any previous instrument. They will measure its exact size, density profile, and redshift distribution. They will allow a precise calculation of how much of the CMB temperature anomaly can be attributed to the ISW effect of the void, and how much remains unexplained. If a significant residual remains after accounting for the void, it will strengthen the case for an additional mechanism, possibly the bubble collision. And if the galaxy surveys reveal additional unexpected structures in the cold spot region, perhaps a clustering of galaxies with unusual properties, or a streaming flow that does not fit the standard model, that will be equally significant. The cold spot is not just a feature in the CMB, it is a feature in a direction in space. Everything we can observe in that direction, from the nearby solar neighborhood to the edge of the observable universe, is potentially relevant to understanding it. This multi-messenger approach to cosmology, combining CMB observations with galaxy surveys and gravitational wave detectors and other instruments, represents the future of the field. No single observation can prove or disprove the most exciting hypotheses. But the combination of many different kinds of observations, each sensitive to different aspects of the physics, can build an evidence base that is very difficult to ignore. The cold spot is a perfect example of why this kind of integrated approach is necessary. A CMB measurement alone cannot distinguish between a supervoid effect and a bubble collision, because both could produce a circular cold region. But add in the polarization pattern, the galaxy distribution, the gravitational lensing of the CMB by the intervening matter, and the statistical properties of the CMB on other scales, and the picture becomes much richer. Each additional piece of information constrains the hypotheses more tightly, until eventually only one survives. That is the vision. Clean, powerful, definitive. In practice, of course, it will be messier. Every new data set will bring new surprises. Every new analysis will open up new questions alongside answering old ones. The process of science is iterative and never fully complete. But the direction of travel is clear. We are moving toward an answer. And whatever that answer turns out to be, it will be profound. Let us now consider one more dimension of the cold spot that deserves careful attention: the implications for our understanding of the Big Bang itself and the period of cosmic inflation. The theory of inflation was proposed by Alan Guth in 1980 as a solution to several problems with a standard Big Bang model. Before inflation, the Big Bang model faced several serious difficulties. One was the horizon problem. Why does the CMB look the same in all directions, even in regions of the sky that, without inflation, could never have been in causal contact with each other? 2 points on opposite sides of the CMB sky are separated by a distance of nearly 93 billion light-years. Light from one side could not possibly have reached the other side in the age of the universe. Yet they have nearly identical temperatures. How? The answer, in Guth's inflation model, is that before inflation, all the regions we can observe were once in causal contact in a tiny volume. Inflation then stretched this volume to cosmic scales in a tiny fraction of a second, carrying the thermal equilibrium with it. After inflation, different regions of the sky were out of causal contact but shared a common thermal history. This explains the uniformity of the CMB. A second problem was the flatness problem. Why is the universe so geometrically flat? In the standard Big Bang without inflation, any initial deviation from perfect flatness would be amplified over time, leading to a universe with either extreme curvature in one direction or the other. The observed flatness of the universe requires incredibly precise fine-tuning of the initial conditions, to something like 1 part in 10 raised to the power of 60. Inflation solves this because it stretches space so enormously that any initial curvature becomes negligible, just as the surface of a balloon, which is curved, becomes locally flat as you inflate it to an enormous size. A third problem was the monopole problem. Grand unified theories predict that the very early universe would have been so hot that magnetic monopoles, exotic particles with a single magnetic pole, would have been produced in large numbers. If the universe cooled down gradually without inflation, we would expect to see many such monopoles today. None have ever been detected. Inflation solves this by diluting the density of monopoles to the point where finding one in the observable universe is essentially impossible. Inflation was initially seen as an elegant solution to these 3 problems, but it quickly became much more than that. It made specific predictions about the properties of the CMB that were subsequently confirmed with extraordinary precision. The pattern of temperature fluctuations in the CMB, the way they are distributed across different angular scales, matches the predictions of inflationary models to a remarkable degree. But inflation is not just one model. It is a framework within which many different specific models exist. Different models of inflation make slightly different predictions about the properties of the CMB, particularly the spectral index, which describes how the amplitude of fluctuations varies with angular scale, and the tensor-to-scalar ratio, which describes the relative contribution of gravitational waves to the temperature fluctuations. The cold spot, if it is not explained by a supervoid or statistical fluctuation, could be a signature of a specific inflationary model that has features beyond the simplest predictions. Some models of inflation predict a period of multiple fields driving inflation, which could leave distinctive features in the CMB that differ from the simplest one-field models. Others predict that inflation ended not completely uniformly, but with some regional variations that could create larger-than-expected temperature anomalies. There is also the question of what happened before inflation, if anything. The standard picture treats inflation as starting at an initial singularity, the Big Bang itself. But some theoretical frameworks suggest that inflation might have been preceded by a different phase, perhaps a period of contraction, or a bouncing universe that collapsed from a previous state. These alternatives to the standard initial conditions can leave distinctive imprints in the CMB, and some researchers have argued that the cold spot might be one such imprint. The pre-Big Bang hypothesis, associated with string theorist Gabriele Veneziano and his collaborators, proposes that the universe went through a phase of contraction before the Big Bang, driven by the dynamics of string theory. In this picture, the Big Bang was not the beginning of time but a bounce, a transition between a contracting and an expanding phase. The CMB in this scenario would carry imprints not just of the inflationary phase but of the contracting phase that preceded it. The cold spot might, in this framework, be a relic of the pre-bounce universe. This idea is highly speculative and is not the mainstream view of most cosmologists. But it illustrates the extraordinary range of physical phenomena that the cold spot has been invoked to explain, and the extraordinary breadth of theoretical ideas that its explanation might require. The honest answer, the scientifically responsible answer, is that we do not know yet. The cold spot is unexplained. Every proposed explanation has problems or gaps. The truth might be one of the existing hypotheses, or a combination of them, or something entirely new that no one has yet thought of. The history of science is full of cases where the right answer turned out to be none of the options that seemed available at the time. The cold spot might be such a case. And that possibility, the possibility of genuine surprise, of being confronted with something so strange that our existing categories are not adequate to contain it, is one of the most exciting aspects of the search. Because genuine surprises are where the deepest discoveries live. Think about how the universe looked to physicists in 1897, the year that J.J. Thomson discovered the electron. They had Maxwell's equations, which described electricity and magnetism perfectly. They had Newtonian mechanics, which described the motion of objects with extraordinary precision. They thought the fundamental questions about the nature of matter were nearly resolved. And then the electron appeared. Then X-rays. Then radioactivity. Then the photoelectric effect. Then special relativity. Then quantum mechanics. The entire edifice of classical physics was transformed in the space of about 30 years, driven by anomalies that no one had expected and that none of the existing theories could explain. We might be at a similar moment now. The standard cosmological model is our most successful description of the universe. It explains an enormous range of observations with great precision. But it leaves open the deepest questions. What is dark matter? What is dark energy? Why does inflation happen? What happened before the Big Bang? Is the universe finite or infinite? Is it the only universe? And the cold spot is right there in the middle of these open questions, a feature that the standard model cannot fully explain. The next generation of observations will not answer all of these questions, but they will answer some of them. And the answers will almost certainly create new questions. That is the nature of scientific progress. Not a march toward a final theory, but a deepening spiral of understanding, where each new discovery reveals not just new answers but new mysteries that previous generations could not even have imagined. To appreciate the full significance of the cold spot, it is worth spending a moment considering what it would mean for human civilization if the bubble collision hypothesis were confirmed. Not just for science, but for culture, philosophy, and the deep human sense of what we are and where we fit in the scheme of things. Throughout human history, our place in the universe has been repeatedly revised downward. We started with the Earth at the center of creation, the special place where an attentive deity had placed humanity. Then Copernicus showed that the Earth orbits the Sun. Then astronomers showed that the Sun is just one of hundreds of billions of stars in the Milky Way. Then they showed that the Milky Way is just one of hundreds of billions of galaxies in the observable universe. Each of these discoveries was a humbling of our sense of cosmic specialness. The multiverse takes this process to its logical extreme. If there are other universes, possibly an infinite number of them, then our universe is not special in any cosmic sense. It is one instance among an incomprehensible multitude. The particular values of the physical constants that allow us to exist are not the result of divine design or fundamental necessity, but of the selection effect that complex, observing beings can only arise in universes with the right properties. Some people find this deeply disturbing. If the universe is not special, if everything that happens in it, every star, every civilization, every act of love or cruelty, is just one instance among an infinity of similar events in other universes, does anything matter? Does our existence have meaning? These are not scientific questions, but they are questions that the science inevitably raises. And they deserve honest engagement rather than dismissal. Others find the multiverse strangely exhilarating. If there are infinite universes, then every possibility is realized somewhere. Everything that can happen does happen. The full richness of possibility is not constrained by the accident of which universe we happen to find ourselves in. The multiverse is not a diminishment of our significance, but an expansion of it, a demonstration that reality is far larger and more varied than we had imagined. And then there are those, perhaps the wisest, who simply hold the question open, who sit with the uncertainty, neither terrified by it nor prematurely resolved, who find in the mystery itself a source of meaning, because a universe that contains mysteries is a universe that invites inquiry, and inquiry is one of the most distinctively human things we do. The cold spot, in this light, is not just a cosmological puzzle. It is a mirror in which humanity sees itself asking its deepest questions. What are we? What is this? Where did it all come from? Is there more? These questions are as old as language and thought. The cold spot gives them new form, new urgency, and the possibility, for the first time in history, of a testable answer. There is one more aspect of the cold spot story that deserves exploration, and that is the way it has been received by the public and the media. Science communication is a complex art, and the cold spot presents particular challenges. On one hand, the possibility of a parallel universe collision is spectacularly exciting and generates enormous public interest. On the other hand, it is a hypothesis, not a confirmed fact, and presenting it as settled science would be deeply misleading. The tension between excitement and accuracy is a constant challenge in science journalism. Headlines about the cold spot have ranged from the carefully hedged, cosmologists study anomaly in the ancient microwave background, to the breathlessly speculative, scientists find proof of parallel universe. The latter type of headline creates a misleading impression and can damage public trust in science when the exciting claim is later qualified or retracted. This matters because public understanding of science has real consequences. When people understand how science works, they are better equipped to evaluate claims about the world, to support evidence-based policy, and to appreciate the genuine achievements of science without being misled by hype or discouraged by uncertainty. The cold spot, handled carefully, is an excellent teaching case about how science actually works. How anomalies are discovered, how hypotheses are tested, how evidence accumulates, and how the scientific community navigates disagreement. The most honest account of the cold spot acknowledges its genuine strangeness, its genuine significance, and its genuine uncertainty. It is strange enough and significant enough to deserve serious attention. And it is uncertain enough that anyone who tells you the answer is already known is either misinformed or oversimplifying. The cold spot is a live mystery, an open question of the highest order. And that is exactly what makes it so compelling. Let us also think about the cold spot from the perspective of what philosophers call the problem of underdetermination. This is the idea that for any body of evidence, there are always multiple hypotheses that are consistent with the evidence. You can never determine the true hypothesis from the evidence alone. You always need additional assumptions or additional evidence to choose between them. The cold spot is a perfect example of this. The evidence is the same, a circular cold region in the CMB. But multiple hypotheses are consistent with this evidence. Supervoid, bubble collision, texture, statistical fluctuation, modification of inflation. No amount of additional examination of the cold region alone, without additional observational data from other sources, can definitively distinguish between these hypotheses. This is not a problem peculiar to the cold spot. It is a universal feature of empirical inquiry. It is why science requires multiple independent lines of evidence, why reproducibility is crucial, why theoretical coherence matters as well as empirical fit. The cold spot is a case where the evidence is currently insufficient to determine the correct hypothesis. The challenge is to design the additional observations that would break the underdetermination. And this is exactly what the next generation of cosmological experiments is designed to do. By providing independent measurements, particularly polarization data, that are sensitive to different aspects of the physics, they will reduce the underdetermination. They will eliminate some hypotheses and strengthen others. They may not provide perfect certainty, because empirical inquiry never does. But they will provide enough evidence that the scientific community can converge on a consensus, and that consensus will represent our best current understanding of what the cold spot is. As we approach the end of this exploration, let us take one final long look at the cold spot and everything it represents. Not just as a cosmological feature or a scientific puzzle, but as a moment in the history of human curiosity. We live in an extraordinary time. For the first time in the history of our species, we have instruments sensitive enough to measure the oldest light in the universe with the precision needed to see subtle features in it. We have theoretical frameworks sophisticated enough to make specific predictions about what different physical processes would look like in that ancient light. And we have the collaborative infrastructure, global teams of scientists, enormous data archives, open source analysis tools, to bring all of this knowledge to bear on a single feature in the sky. The cold spot is the product of all of that. It is the intersection of the universe's 13-billion-year-old history with humanity's 21st century science. It is the moment where the very small, the quantum fluctuations of the earliest universe, meets the very large, the possible collision of entire universes. And it is the place where the fundamental question of our cosmic uniqueness, whether our universe is all there is, becomes not just philosophical but potentially testable. Whether the cold spot turns out to be a statistical fluke, a supervoid, or a scar from a collision with another universe, its exploration will have advanced our understanding of the cosmos in ways that matter. Every hypothesis that has been proposed has generated new theoretical insights. Every observation has refined our picture of the universe's structure. Every argument has sharpened our thinking about what evidence can and cannot tell us. And when the answer finally comes, whether it comes in the next decade from the Simons Observatory or CMB-S4, or whether it comes in the next century from instruments we cannot yet imagine, it will be a triumph not just of science but of human curiosity, of the irresistible, entirely irrational, and profoundly beautiful human need to look at the unknown and ask, what is that? The cold spot sits there in the ancient sky, cold and patient and strange, waiting for us to become clever enough, or lucky enough, or persistent enough to understand it. And in its waiting, it asks us the deepest question any feature of nature has ever asked. What lies beyond the boundary of everything you know? Perhaps there is another universe out there, vast and strange, whose history briefly intersected with ours billions of years ago, leaving behind a faint, cold circle in the light of creation. A universe with different stars, different physics, possibly different forms of complexity and consciousness, completely inaccessible to us, forever separated by the expanding space between bubble worlds. A universe that touched ours once, briefly, and left behind the equivalent of a fingerprint on the glass of our cosmic window. Or perhaps the cold spot is something we already understand in principle but have not yet precisely measured. A vast desert in the cosmic web, a billion light-year void, whose gravitational emptiness has left a cold shadow on the ancient light. A feature that, while remarkable in its scale, falls within the expected range of a universe as old and as vast as ours. Or perhaps it is something else entirely. Something no one has yet imagined. Something that will require ideas that do not yet exist, concepts that have not yet been invented, a future generation of physicists who will look back on our current confusion with the same gentle condescension with which we look back on those who struggle to accept that the Earth moves around the Sun. The history of science is a history of exactly this. Ideas that seemed impossible becoming obvious. Mysteries that seemed insoluble becoming textbook entries. Questions that seemed unanswerable becoming the foundations of new fields. The cold spot will have an answer eventually. And when it does, that answer will open new doors, reveal new mysteries, and send new generations of curious minds racing into new unknowns. That is the story of science. That is the story of the cold spot. A story still being written, in data from the oldest light in the universe, by the most persistent and the most curious species that this particular bubble universe has ever produced. And if you walk outside on the next clear night and look up at the sky, somewhere in the direction of the faint, winding constellation Eridanus, the river, there is a patch of ancient light that is a little bit colder than everything around it. A small, circular whisper in the fabric of the cosmos. A question mark written in the language of photons that have been traveling since before the Earth existed. A feature so strange that the most creative minds in science have spent 20 years trying to explain it and have not yet succeeded. It is up there right now, cold and mysterious and patient. And somewhere on Earth, at this very moment, there is a scientist looking at the data, running the calculations, writing the code, designing the next experiment that will finally tell us what it is. And when they find the answer, it will either confirm something remarkable that we already suspected, or it will surprise us with something we never imagined. Either way, the universe will be stranger and more wonderful for the knowing of it. And that is the cold spot. Not just an anomaly, not just a puzzle, but an invitation to go further, to look deeper, to ask harder questions, to reach beyond the edges of what we know into the vast, cold, beautiful, incomprehensible mystery of what we do not. The question is not just what created the cold spot. The question is what we will discover when we finally find out, and whether the answer will be the beginning of the next great adventure in the long and extraordinary story of human understanding of the cosmos. We stand at the edge of the observable universe, peering into the ancient light of creation, and we see something strange, something cold, something circular, something that should not be there, or should not be as large, or should not be as cold, or might be exactly what the most audacious theory in modern physics predicts. Something that might be the imprint of another universe. And the only honest thing we can say, with everything we know, is this: we do not know yet. But we are close. And whatever we find, it will be extraordinary. Now let us go even further, because the story of the cold spot does not exist in isolation. It is part of a larger tapestry of mysteries and discoveries that together paint a picture of a universe far more complex, far more layered, and far more strange than anything our ancestors could have imagined. And by understanding the context in which the cold spot sits, we can appreciate not just what it might be, but what it tells us about the frontier of human knowledge. For centuries, astronomers looked at the night sky and saw stars, points of light, beautiful and mysterious, but seemingly fixed in their positions relative to each other. Then came the realization that these points of light were suns, some larger and brighter than our own, some smaller and dimmer, arranged in a galaxy that itself was enormous beyond easy comprehension. Then came the realization that our galaxy was just one among billions. Then came the understanding that the universe had a beginning, a moment of creation 13.8 billion years ago, and that it had been expanding and cooling ever since. Each of these realizations was a revolution. Each one expanded the scope of what we knew and deepened the mystery of what we did not. And each one happened because someone looked at the data more carefully, asked a harder question, or built a better instrument. The cold spot is the latest in this series of moments where the universe reveals, through careful observation, that it is not quite what we thought it was. The relationship between the CMB and the large-scale structure of the universe is one of the most fascinating areas of modern cosmology. The CMB is a map of the universe at 380,000 years old. The large-scale structure, the web of filaments and voids and clusters that we observe today, is the grown-up version of the patterns that were imprinted in that early universe. The seeds of every galaxy, every cluster, every void, were already present in the CMB. By comparing the CMB map with the observed large-scale structure, cosmologists can reconstruct the history of how structure grew and test whether the standard cosmological model's predictions about that growth are correct. So far, the agreement has been remarkably good. The Lambda CDM model predicts the distribution of galaxies on large scales, the power spectrum of the CMB, the relationship between galaxy cluster masses and their abundance, and many other observables, with an accuracy that is extraordinary given the model's relative simplicity. It uses only 6 free parameters to describe the entire observable universe from the Big Bang to the present. That is a remarkable achievement. But there are tensions. In addition to the cold spot and other CMB anomalies, there is a growing discrepancy between 2 different ways of measuring the expansion rate of the universe, called the Hubble constant. When this rate is measured using the CMB and early universe physics, it gives a value of about 67 kilometers per second per megaparsec. When it is measured using local observations of supernova distances and Cepheid variable stars, it gives a value of about 73 kilometers per second per megaparsec. This discrepancy, called the Hubble tension, has grown steadily more significant as the measurements have become more precise, and it is now at a level of about 5 sigma, which is the threshold typically used in physics to claim a discovery. The Hubble tension might be a systematic error in one or both measurements, or it might be evidence that the standard cosmological model is missing something. If the model is missing something, the same missing ingredient might also contribute to the CMB anomalies, including the cold spot. Some researchers have proposed modifications to the early universe physics, such as the introduction of a new light species of particle or a period of early dark energy, that could simultaneously resolve the Hubble tension and explain some CMB anomalies. These proposals are speculative but are being actively tested. The possibility that the Hubble tension and the CMB anomalies are connected is particularly exciting. If they are, then the solution to one might unlock the solution to the other. And a solution that explains both would be a much more compelling argument for new physics than a solution that explains only one. The cold spot, in this context, is part of a web of tensions and anomalies that collectively suggest that our standard model of cosmology, as successful as it is not the final word. We should also take a moment to appreciate the technological marvel that has made all of this possible. The instruments used to study the CMB are among the most sensitive ever built. The Planck satellite, for example, carried a focal plane cooled to a temperature of 0.1 Kelvin, 1/10 of a degree above absolute zero, to minimize thermal noise in the detectors. Its bolometric detectors were sensitive to variations in the CMB temperature of as little as a few millionths of a degree. It took data continuously for 4 years, scanning the entire sky multiple times. The data from Planck alone is terabytes in size. Analyzing it requires sophisticated algorithms, powerful computers, and enormous amounts of human expertise. The data processing pipeline for a modern CMB experiment involves thousands of steps, from calibrating the detectors and removing instrumental artifacts to subtracting the contribution of foreground sources like dust in the Milky Way, to producing the final clean CMB maps. Every step requires careful validation and cross-checking. The final maps that scientists use to study the cold spot and other features are the product of years of careful work by hundreds of people. When we look at a CMB map and see the cold spot, we are not seeing a simple, direct measurement. We are seeing the result of an enormously complex chain of inference, from photons hitting a detector 1.5 million kilometers from Earth, through years of data processing, to a false color image on a computer screen. The fact that this chain of inference is reliable, that the cold spot appears consistently across different instruments, different analysis pipelines, and different processing assumptions, is a testament to the extraordinary rigor and care of the scientists involved. And yet, at the end of this chain of inference, we still do not know what the cold spot is. We have ruled out some explanations. We have found hints in the direction of others. But we do not yet have the smoking gun. And this is honestly where we are. Not at the end of the story, but somewhere in the middle. At a moment of suspense and uncertainty and extraordinary potential. The cold spot is a reminder that the universe is not obliged to be simple. It is not required to conform to our favorite theories or our preferred narratives. It is what it is, and our job is to figure out what that is with the best tools at our disposal. Sometimes that process is swift and satisfying. Sometimes it takes decades. Sometimes it takes generations. But it always works in the end. Not because science has some guaranteed path to truth, but because reality is consistent. The universe behaves the same way whether we are looking at it or not. Its features have explanations, even if finding those explanations requires patience, creativity, and the courage to consider ideas that seem wild or impossible. The cold spot has an explanation. We just have not found it yet. But we are looking. And we are getting better at looking every year. There is something beautiful in that. In the image of thousands of scientists around the world, working on different pieces of the puzzle, sharing their data and their ideas and their criticisms, driven by nothing but the desire to understand. Not for money, not for power, not for fame in the conventional sense, but for the extraordinary, irreplaceable satisfaction of knowing something true about the universe, of having looked at the cosmos and understood a little more of what it is. The cold spot is a gift to that enterprise, an anomaly that resists easy explanation, that demands creativity and rigor and collaboration, an anomaly that just might, be telling us something so profound that it changes everything, or that might, more humbly, be teaching us something important about the limits of what we know. Either way, it is worth understanding. And the effort to understand it is among the most noble things our species has ever undertaken. So the next time you look at the sky, whether you know the constellation Eridanus or not, whether you can point to the exact region of the cold spot or not, take a moment to appreciate what is up there. Not just the stars and the galaxies and the faint glow of the Milky Way, but beyond all of that, at the very edge of what light can carry to us, there is the ancient glow of the Big Bang itself. And in one small, cold, mysterious patch of that glow, there is a question that the universe has been waiting 13.8 billion years for something clever enough to ask. The answer is coming. Not today, perhaps. Not this year. But it is coming. Because that is what human curiosity does. It pushes and reaches and builds and calculates and questions until the unknowable becomes known. Until the mystery becomes understanding. Until the cold spot, strange and silent and cold, finally reveals what it has been hiding all this time. And when it does, the story will not end. It will begin again. Because that is how the universe works. And that is how science works. And that is how we work. We ask, and we look, and we find, and we ask again. Forever reaching into the dark and cold of the unknown, searching for light. The cold spot exists. It is real. And whatever it is extraordinary. And we are the species that found it. And we are the species that will eventually explain it. That is not a small thing. That is, in fact, one of the greatest things that any mind has ever attempted. And perhaps that is the most important thing the cold spot tells us. Not about the universe, but about ourselves. That we are here on this small and fragile planet, in this ordinary galaxy, in this particular bubble of space and time, and we look up. We look out. We look back to the beginning of everything. And we ask. We always ask. And sometimes, just sometimes, the universe answers. The cold spot is still waiting for its answer. And somewhere right now, in a lab or at a computer or under the dark skies of the Atacama Desert, someone is working toward it. Patient, persistent, curious, and driven by the same impulse that has always driven our species forward into the unknown, the unquenchable need to understand. That is the story of the cold spot. A story still being written. in the oldest light in the universe, and in the newest ideas in human science. And it is a story worth following, because wherever it leads, it will take us somewhere we have never been before. And that, in the end, is the most extraordinary thing any story can do. Now we must travel even deeper into the theoretical landscape that surrounds the cold spot, because there are dimensions of this mystery that we have touched on but not fully explored. And each of them adds another layer of richness to what is already one of the most compelling puzzles in the history of cosmology. One dimension that deserves careful attention is the relationship between the cold spot and quantum mechanics. At first glance, quantum mechanics and cosmology seem like strange bedfellows. Quantum mechanics describes the behavior of particles at the smallest scales, where uncertainty and probability reign. Cosmology describes the behavior of the universe at the largest scales, where classical physics and general relativity seem to be the right tools. But in the very early universe, at the moment of inflation, these two domains were intimately connected. The quantum fluctuations that inflation stretched to cosmic scales were not classical random variations. They were genuine quantum fluctuations, arising from the Heisenberg uncertainty principle, which states that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. In the inflationary universe, the field driving inflation, called the inflaton field, underwent quantum fluctuations on all scales. These fluctuations were then stretched by the rapid expansion of space to scales much larger than the quantum realm, where they became classical density fluctuations that seeded the formation of structure. The translation from quantum to classical during inflation is not perfectly understood. It is one of the deep foundational questions in quantum cosmology, but it has a profound implication. The large-scale structure of the universe, including the distribution of galaxies and the pattern of the CMB, is ultimately a product of quantum mechanical processes. The universe we see is, in a very real sense, the amplified quantum foam of the inflationary epoch. And the cold spot might be an extreme manifestation of this quantum origin. If the quantum fluctuations during inflation happen to produce an unusually large underdensity in one region, that region might have evolved into both the supervoid we observe and the CMB cold spot above it. The chance of such a large fluctuation is small but not zero. And in a universe as large as ours, small probabilities become near certainties somewhere. But the quantum origin of structure also connects to the multiverse in a subtle way. In the many worlds interpretation of quantum mechanics, every quantum fluctuation gives rise to a branching of the universe into all possible outcomes. The quantum fluctuations of inflation would thus give rise to an enormous, possibly infinite, number of branches, each with a different realization of the large-scale structure. In most branches, the CMB would look roughly like what we observe, with small temperature variations distributed according to the statistical predictions of inflation. In a tiny fraction of branches, large anomalies like the cold spot would appear. We find ourselves in a branch with such an anomaly not because it is probable but because of the selection effect of our own existence. This is a strange kind of explanation, and many physicists find it unsatisfying precisely because it explains everything. If every possible configuration exists somewhere in the many worlds multiverse, then no specific configuration requires a further explanation. The cold spot exists because all possible CMB maps exist. This is technically consistent, but feels like a non-answer. The challenge is to find a more specific, more constrained explanation that makes the cold spot not just possible but predicted. This is the essential challenge of cosmology at the frontier of our knowledge. The universe is large enough, and our theories are general enough that almost anything can be made to fit within them with sufficient ingenuity. The scientific progress comes from finding the one explanation that not only fits the current data but also makes new, specific predictions that can be tested. The bubble collision hypothesis does this, as does the supervoid hypothesis, as does the texture hypothesis. Each makes specific predictions about the polarization, the shape, the depth, and the additional large-scale structure associated with the cold spot. Future observations will test these predictions, and the explanations that fail those tests will be eliminated. The remaining explanations will then make further predictions about other features of the CMB, about the distribution of galaxies in the cold spot direction, about the lensing of CMB photons by intervening matter, and so on, until the explanation has been tested so thoroughly that it becomes as reliable as any established fact in science. That process takes time. It takes patience. It takes resources. And it takes the kind of sustained, collective commitment to understanding the truth about nature that is one of the most admirable things our civilization has ever managed to maintain. The community of cosmologists working on the CMB and the cold spot is part of that commitment. And their work is a gift to every human being who has ever looked at the sky and wondered. The cold spot is also deeply connected to one of the most profound and troubling questions in modern cosmology, the question of fine-tuning. The physical constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, the value of the cosmological constant, appear to be extraordinarily well tuned for the existence of complex structures like stars, planets, and life. Small changes in any of these constants would lead to a universe in which atoms could not form, or stars could not burn, or galaxies could not coalesce. The universe appears to be exquisitely configured for complexity. This fine-tuning has two broad categories of explanation. The first is that there is some deep principle of physics that requires these constants to have these values, a principle that we have not yet discovered but that a final unified theory would reveal. The second is the multiverse. In a sufficiently large and varied collection of universes, some will have the right constants by chance, and we find ourselves in one of those because only those universes contain observers. The cold spot, if it is evidence of a bubble collision, supports the second explanation. It suggests that the multiverse is real, that other bubble universes with potentially different constants exist, and that our universe is one instance among many. This does not prove that the fine-tuning is explained by the multiverse, but it does lend credibility to the overall framework in which such an explanation lives. If the cold spot is explained by something within our universe, a supervoid or a statistical fluctuation, then the evidence base for the multiverse is weaker. Not impossible, because the multiverse hypothesis has many other theoretical motivations, but less empirically supported. The cold spot is thus relevant not just to the question of what caused it, but to the broader question of the structure of reality itself. This is a remarkable situation. A temperature anomaly in a satellite dataset, found by cosmologists looking at maps of microwave radiation, has implications for one of the deepest philosophical and scientific questions ever asked. Does this universe exist by necessity or by chance? Are we inevitable or are we lucky? Is there a reason for everything, or are we the accidental inhabitants of one universe in an uncountable sea? The cold spot cannot answer these questions by itself. No single observation can, but it is a clue. A piece of evidence in a case that will take the combined efforts of the world's scientific community, across multiple generations, to fully solve. And it is a remarkable thing that we have such a clue at all. That the universe has left, in the oldest light we can observe, a feature that might point us toward the answer to the biggest question we have ever asked. Some critics of the multiverse hypothesis argue that it is not just unscientific but dangerous. That by providing an answer to fine-tuning questions that requires no specific mechanism, no testable prediction, no falsifiable hypothesis, it removes the incentive to search for a deeper, more fundamental explanation. If the constants are what they are because of selection effects in a multiverse, why bother trying to derive them from first principles? Why not just accept that we live in the universe we live in, and that other universes are not our business? This is a genuine concern, and it reflects a real tension within theoretical physics. The multiverse is, in some sense, the easiest possible answer to hard questions. It is tempting to use it as a universal solvent, dissolving every problem of fine-tuning or unexplained coincidence in a sea of possible universes. But science advances by finding specific, constrained explanations, not universal ones. The best response to this criticism is that the multiverse is not just a philosophical position. It is a scientific hypothesis that makes specific predictions, including the existence of bubble collision signatures in the CMB. If those signatures are found, the multiverse becomes empirically supported, not just theoretically motivated. And if they are not found, the hypothesis is weakened. This is science done correctly. The multiverse, controversial as it is engaging with empirical reality through the cold spot. And that engagement is exactly what science should do. The search for the explanation of the cold spot is also a search for the limits of science. What can we know about the universe? What is in principle knowable, and what is forever hidden beyond the cosmic horizon? These are not just philosophical questions. They have practical implications for how we structure scientific research, how we allocate resources, and how we evaluate the success or failure of theoretical frameworks. The cosmic horizon, the boundary of our observable universe, is a fundamental limit on what we can directly observe. We cannot see beyond it, because light from beyond it has not had time to reach us. And if other bubble universes are beyond that horizon, we can never observe them directly. We can only infer their existence from their effects on the physics within our horizon, effects like the cold spot. This means that the evidence for the multiverse will always be indirect. We will never take a picture of another universe. We will never receive a signal from one. The best we can hope for is exactly what the bubble collision hypothesis offers: a specific, predictable imprint on our CMB, consistent with what theory predicts and inconsistent with all other explanations. That is not certainty. But in science, certainty is rare. What we have instead is degrees of confidence. And the current degree of confidence in the bubble collision hypothesis, while tantalizing, is not yet high enough to call it science. But it is high enough to call it worth pursuing. And that is what the scientific community is doing. Pursuing it with the best instruments, the most careful analysis, and the most creative theoretical thinking that our civilization can bring to bear. As we look to the future, there is one more direction worth exploring. The possibility that advances in quantum gravity could shed new light on the cold spot. Quantum gravity is the as-yet unachieved theory that would unify quantum mechanics and general relativity. It is arguably the most important open problem in theoretical physics. And it is intimately connected to the physics of the very early universe, where both quantum effects and gravitational effects were equally important. In the Planck era, the first 10 raised to the negative 43 seconds after the Big Bang, the universe was so dense and so hot that a quantum theory of gravity is required to describe it. Our current theories break down completely at this point. The singularity of the Big Bang, the mathematical point of infinite density and temperature, is not a real physical feature of the universe, but a symptom of the inadequacy of our theories at extreme conditions. A successful quantum gravity theory would tell us what happened at the Planck era. It might reveal that the Big Bang was not a singularity, but a smooth quantum transition, perhaps a bounce from a previous phase. It might reveal that space and time are not fundamental, but emergent from more basic quantum structures. It might tell us whether bubble universes can nucleate and collide, and what such a collision would look like in the CMB. Loop quantum gravity, one of the leading candidates for a quantum gravity theory, predicts that space has a discrete, granular structure at the Planck scale, with a minimum length of about 10 raised to the negative 35 meters. In this framework, the Big Bang singularity is replaced by a quantum bounce, a transition from a contracting universe to an expanding one. The cold spot might carry information about this pre-bounce phase, if the quantum effects during the bounce were large enough to leave imprints that survived inflation. String theory, the other leading candidate for quantum gravity, predicts that the fundamental constituents of the universe are not particles but tiny vibrating strings of energy, existing in a space of 10 or 11 dimensions. The extra dimensions are curled up so small that we cannot detect them with current instruments. Different ways of curling up these extra dimensions correspond to different vacuum states of string theory, and different bubble universes in the string theory landscape might have different compactifications. A bubble collision might carry information about the properties of the colliding bubble's compactification, encoded in the detailed temperature and polarization profile of the cold spot. This is highly speculative, but it illustrates the deep connections between the cold spot and the most fundamental questions in theoretical physics. The cold spot sits at the intersection of many of the most important unsolved problems in science. It is, in a very real sense, a focal point of the frontier of knowledge. And it is a focal point that humanity stumbled upon not because we were looking for it, but because we were carefully and patiently measuring the universe. The cold spot was not predicted. It was not designed. It emerged, stubborn and strange, from the data. And it has refused to go away or explain itself for more than 20 years. In the vocabulary of human discovery, the cold spot is the equivalent of a locked door in a house you thought you knew perfectly. You were sure you knew every room, every corner, every feature of the structure. And then one day you find a door you never noticed before. And behind it, you can hear something. Not a sound exactly. More like a very faint, very cold breath. Something that suggests whatever is behind the door is real, and possibly enormous, and possibly unlike anything you have ever seen. The question is, do you open the door? And the answer for science is always yes. Because whatever is behind the door is part of reality, and reality is what science is for. The next experiments will try to open that door. With better detectors, sharper maps, more precise statistics. They will probe the polarization around the cold spot. They will map the galaxy distribution in the cold spot direction with unprecedented detail. They will measure the lensing of the CMB by the supervoid. They will search for additional anomalies in the CMB that might be related to the cold spot. And from all of this, they will piece together the most complete picture yet of what the cold spot is. It might be a supervoid and nothing more. A cosmic desert, vast and ancient, whose gravitational signature has been misinterpreted as something more exotic. That would be a valuable result. It would tell us about the distribution of matter in the universe and the properties of dark energy. It would confirm or challenge the standard cosmological model in a specific and important way. It might be evidence of a bubble collision, a mark left by the only interaction our universe has ever had with another universe. A fingerprint of a moment when two realities briefly touched, 13.8 billion years ago, leaving behind in the ancient light a circular, cold reminder of an event we can barely conceive. That would be the most extraordinary discovery in the history of science. Or it might be something we have not yet imagined. A category of phenomenon that exists in no current textbook, arising from physics that no living scientist has yet formulated. A discovery that sends the entire field racing in a new direction, generating new questions that make today's questions seem simple by comparison. That too would be extraordinary. In fact, that might be the most extraordinary outcome of all. Because the history of science shows that the most transformative discoveries are almost always surprises. Not confirmations of what we expected, but revelations of what we never imagined. The electron was a surprise. Radioactivity was a surprise. The expansion of the universe was a surprise. Dark energy was a surprise. And the cold spot, whatever it turns out to be, will almost certainly teach us something we did not expect. The universe is not in the business of confirming our expectations. It is in the business of being what it is. And what it is, as far as we have been able to determine, is vastly stranger and richer and more wonderful than our best theories have been able to capture. The cold spot is a reminder of that. A reminder that the universe still has secrets. That the map of what we know is small compared to the territory of what exists. That somewhere in the ancient light of creation, there are patterns we have not yet learned to read. And we are the species that is trying to read them. That has always tried to read them. That cannot stop trying, because curiosity is as fundamental to us as breathing. We read the patterns in the stars for navigation, for agriculture, for mythology, for the pure joy of understanding. We read the patterns in the atoms for medicine, for materials, for technology. And now we read the patterns in the ancient light of the Big Bang for the deepest knowledge of all. The knowledge of where we came from and whether we are alone. The cold spot is our current sentence in that reading. Strange and incomplete, offering multiple possible translations, demanding the best scholarship we can bring to bear, and rewarding that scholarship, not yet with a final answer, but with the extraordinary gift of a question worth asking. In the end, The Cold Spot is a story about what it means to be alive in a universe that is too large and too strange to fully comprehend, but just comprehensible enough to keep asking questions about. It is a story about the long reach of human curiosity, stretching across 13 billion years of cosmic history to ask, what made you? And whether our universe is the only universe. And whether, somewhere in the oldest light we can observe, there is a message from a world beyond our own. That question is alive. That message, if it is real, is there. And we are here, asking. And that combination, the question, the possible answer, and the questioners, is one of the most remarkable things the universe has yet produced. The cold spot waits. Cold, ancient, circular, and strange. In the direction of Eridanus, the river, pouring its ancient light across the sky. In the oldest glow of creation. In the boundary between what we know and what we do not. In the silence at the edge of everything. And somewhere in that silence, if we listen carefully enough, if we build sensitive enough instruments and do careful enough mathematics and ask the right questions with the right tools, we might hear the echo of another world. Another universe, pressing faintly against our own, leaving behind, in the oldest light in all of existence, the faintest possible cold whisper, I was here. We are listening. And whatever we hear, it will be worth hearing. Because it will be the universe telling us, in the only language it has, the truth about what it is. And we, who are made of the universe's own matter, thinking the universe's own thoughts, standing on one of the universe's billions of planets and looking up at its ancient light, will finally understand just a little more of what we are part of. And that understanding, however partial, however provisional, is among the most precious things that any mind has ever achieved. The cold spot exists. The mystery is real. The search is ongoing. And the answer, whatever it turns out to be, is waiting, patient and cold and ancient, in the light of the Big Bang itself. We just have to keep looking, and asking, and reaching, into the dark and the cold and the beautiful unknown. Because that is what we do, and that is who we are. Children of the universe. Heirs of 13 billion years of cosmic evolution. The creatures that the cold spot made, who are now trying to understand the cold spot itself. And if that is not the most extraordinary story in the history of the cosmos, it is hard to imagine what would be. Now, as we prepare to draw this exploration toward its close, there are a few final threads worth pulling together, because the cold spot does not exist in isolation, and its meaning is enriched by understanding everything that surrounds it and everything that it points toward. One of the most important things the cold spot teaches us is about the nature of evidence at the cosmic frontier. We live in an age of big data. Modern science generates more data than any previous generation of humans could have processed or even stored. The CMB alone, as mapped by Planck, represents a dataset of extraordinary richness. The galaxy surveys under construction or already operating will add many more orders of magnitude of data. And with all of this data comes a new kind of challenge. How do we extract meaningful signals from an ocean of numbers? The cold spot is an example of an anomaly that sits at the edge of what the data can clearly tell us. It is significant enough to be noticed, robust enough to survive multiple independent analyses, and large enough to demand explanation. But it is subtle enough that its significance depends critically on the statistical methods used and the assumptions made in the analysis. In this sense, it is a perfect test case for the development of better methods in cosmological data analysis. Machine learning and artificial intelligence are beginning to play a role in this analysis. These tools are extraordinarily good at finding patterns in large datasets, patterns that human analysts might miss. Several groups have already applied machine learning methods to the CMB, looking for anomalies beyond those found by traditional methods. Some of these analyses have found additional hints of large-scale anomalies, potentially related to the cold spot. Others have found nothing new. The field is still developing the tools and the expertise to fully exploit these methods. In the next decade, AI-assisted analysis of CMB data will likely become standard, and it is possible that AI will find in the CMB data features that human analysts have missed, features that could shed new light on the cold spot and other anomalies. This is an exciting prospect, not because AI can somehow transcend the limits of the data or discover things that are not there, but because it can process vast amounts of information more efficiently and objectively than human analysis, finding subtle correlations and patterns that are easy to overlook. The combination of AI analysis, next-generation experiments, and improved theoretical frameworks puts us in a remarkably strong position to make progress on the cold spot mystery in the coming years. The optimism in the field is palpable. Not the naive optimism of people who expect easy answers, but the informed optimism of researchers who can see the tools being assembled that will finally be adequate to the challenge. There is also a social dimension to the cold spot story that is worth acknowledging. The researchers working on this problem are a global community, spanning dozens of countries and institutions. They communicate across language barriers, time zones, and cultural differences, united by the common language of mathematics and the common commitment to understanding the universe. The papers on the cold spot have been written by authors from the United States, the United Kingdom, Spain, Finland, India, Italy, the Netherlands, Germany, Japan, and many other countries. The data comes from satellites and telescopes built by international collaborations. The analyses are shared openly, and the debates are conducted in the open literature. This is science at its best: collaborative, international, transparent, and driven by the search for truth rather than national or institutional advantage. The cold spot is a problem that no single country or institution can solve alone. It requires the full range of human intellectual capacity, combined in a way that is possible only in a connected, communicating civilization. In this sense, the cold spot is not just a scientific puzzle. It is a demonstration of what humanity is capable of when it works together on a question larger than any individual or group. It is a reminder that the things we share, the curiosity, the intelligence, the desire to understand, are more profound and more powerful than the things that divide us. And perhaps that is another reason why the cold spot matters. Not just because of what it might tell us about the universe, but because of what the search for its explanation reveals about us. About our capacity for sustained, collective intellectual effort. About our willingness to confront uncertainty without losing the courage to keep asking. About our instinct to look up, to look out, and to wonder. The universe gave us the cold spot, and in trying to understand it, we are giving the universe something back. The gift of a mind that notices, that questions, that persists. A mind that refuses to accept mystery as the final answer, that keeps building and measuring and calculating until the unknown becomes known. That is the human project. And the cold spot is, right now, one of the places where that project is most alive, most urgent, and most thrilling. So we return to where we began. A night sky, impossibly vast, impossibly beautiful. Somewhere in that sky, in the direction of a faint and winding constellation, in the oldest light that exists, there is a region that is colder than it should be. Circular, large, anomalous, and unexplained. A whisper from the edge of creation. A question written in the language of ancient photons, asked by the universe of itself, and still waiting for an answer. We have spent these pages exploring every dimension of that question. The physics of the cosmic microwave background, the discovery of the cold spot and the history of its investigation, the supervoid hypothesis and its limitations, the bubble collision hypothesis and the theory of the multiverse, the texture hypothesis and cosmic topology, the Hubble tension and the broader crisis of standard cosmology. the future experiments that will try to resolve these mysteries, the philosophical implications of parallel universes, the human stories of the scientists who are doing this work. And through all of it, the cold spot has remained exactly what it is: strange, cold, real, and unexplained. A feature of the universe that demands our best thinking and refuses to yield to our existing theories. A feature that might be the most mundane anomaly in cosmology, or the most profound discovery in the history of science. We do not know yet, and in that not knowing, there is something profound. A reminder that the universe is larger than our knowledge of it, that the cosmos has depths we have not yet plumbed, that the light of the Big Bang, falling on our instruments after 13.8 billion years of travel, still carries secrets that we are only beginning to learn to read. The cold spot is one of those secrets, and it is, in every sense of the word, extraordinary. Think about that the next time you look up at the night sky. Somewhere up there, in the ancient microwave glow that permeates all of space, invisible to the naked eye but real and measurable, there is a cold circle, a cosmic mystery, a possible fingerprint of another universe. And somewhere down here, a small army of curious and devoted human beings is working every day to understand it. We are the universe becoming aware of itself. We are the atoms of the Big Bang, arranged just so, asking questions about where they came from. And the cold spot is the universe's most enigmatic answer so far. Not a clear answer. Not a comfortable answer.